Okay, so picking up where we left off, we're going to be talking about the Sylow theorems today. So the last sort of big thing we did, moving over here for a moment, is that if you have a finite group G, which is divisible by P, then G has an element of order P. And the proof of this, so last time we proved a bunch of stuff about P groups and orbits and all that kind of stuff, and the proof of this was a classic kind of orbit counting game with G acting on some set X. So I won't go over it again, it's right here, but the idea is that when you have a prime, especially with prime numbers occurring, divisibility relations are easy to come by or hard to come by if that's what you want, and you can often leverage that into getting a lot of interesting stuff. Okay, so anyway, today is going to be an example, some tour de force examples of that, known as the Sylow theorems. So I kind of ended last lecture by saying that what we were going to do is generalize this theorem to say that not only are there subgroups of order P, but there are subgroups of order P to the n for any n that divides G. So this theorem is called the first Sylow theorem. So I'll just pick up right where I left off and say this is the first Sylow theorem. So it's the famous theorem in finite group theory. Okay, and we're ready, given what we know from last time, we're ready to prove it. So let's do it. So this goes by induction. There exists, let's call it H prime in G, such that the order of H prime is P to the n minus 1. So n is a number at least 1. When n is 1, the base case of the theorem is exactly the previous theorem. There exists an element of order P. The cyclic subgroup it generates is a subgroup of order P, right? So when n is 1, you're done by the previous theorem. And so now we can just immediately jump into the induction. Okay. So what we're going to do is we're going to look at the coset, the left multiplication action of H prime on G. And we're going to look at the action of that actually on the coset space G mod H. So G mod H prime, excuse me. So here's what we're going to look at. So G mod H prime has a left action of G. Right, so you can take this coset space. Remember, you quotient out by the equivalence relation where you identify things under multiplication in H. Right multiplication, right? Because I'm going mod H on the right here. And then the resulting thing has a left action by G, right? I could still take an element of G and multiply it by any coset, any equivalence class, and get another equivalence class. And so it has a left action of H prime in G. Right? That's just tautological. If I have an action of G, I have an action of any subgroup of G on the same set. Okay, so let's look at so we're going to look at the elements are sort of cosets for H prime, and so we're going to look at the following question: when are you fixed under H prime? So let's look at. So the key to the proof is to look at when is H prime times XH prime equal. Right, so the X times H prime, that's a coset, that's an element of this G mod H prime. And now the question is, when is that fixed under the action of H prime? And the answer is, it's if and only if H prime is X H prime for all H and H prime. Okay, that's just tautology. You're just literally writing out what does it mean if this times this to equal this as sets. It means that, right? And so then this is if and only if X inverse H, right? X inverse H X times H prime is equal to H prime, right? So it's if and only if. Okay, so this times H prime is equal to H prime. If you look at the identity element in H prime, that's X inverse XH times the identity is in H prime. So this, in fact, can be reformulated even more easily as this element being inside H prime, right? Just by looking at the action on the identity. So okay, so what does that mean? That's something. That's a statement, right? That says that when I conjugate by X inverse, then I remain, just to be clear, this is for all H and H prime. So when I conjugate by X inverse, I'm remaining in H prime. Okay, so let's make a statement. So let's pause the proof and give an important definition, which we haven't talked about before. The normalizer of, I'm going to follow Goodwin's notation in here. So he calls it the normalizer sub G of H prime is the set of all G and G such that G, quote unquote, normalizes H. So right, so G, H, G inverse is equal to H. Okay, so the normalizer is the set of things in G that, I'm calling this subgroup H prime, not H. The set of things in G that take H to itself under the conjugation action. So it's the stabilizer of H, this group H prime, under the conjugation action. So it's a subgroup of G in which H prime is normal. So it's the largest, in fact, let's just say, kind of clearly, it's the largest subgroup of G in which H prime is normal. So that's the reason for the name. Right? It's exactly the set of things that make H prime a normal subgroup. Right? Normal means that you're fixed under this conjugation action. Okay? So that's the normalizer. All right, so pause. So let's return to the proof. So where did we land? We landed at some statement X inverse HX is in H prime for all H and H prime. Well, that looks like X inverse is a normalizer. Right? So XH prime is fixed under the action of H prime. Right? So what's the setup? This coset XH prime is fixed under the left action of this H prime if and only if X is in the normalizer inside G of H prime. Right? So that's the upshot here. Okay? All right, so this all seems maybe a little bit of abstract stuff, but the point is we're gonna start doing these prime number conditions are going to come out in various orbit counting exercises, and we need to know what orbits are we looking at, what information do we have. So the answer is we're going to look at the action of H on G mod H. Okay, and now we're going to say, okay, so we note that the size of G mod H is divisible by P. Okay, because, again, this is supposed to be H prime, precisely because the size of H prime is P to the n minus 1 is less than P to the n, right? We know that P to the n divides the size of G, right? This prime is factoring into G, and we're saying the size of H prime is some smaller prime power. So the quotient here is divisible by P. Okay, on the other hand, so this is divisible by P. On the other hand, every non-fixed point, let's put it this way. Also, every orbit O, which is not a single point, and when I say every orbit, I mean the orbits of H prime on G mod H, right? So every orbit of O of H prime acting on G mod H prime, right, which is not a single point, has size divisible by P. Well, I mean, H prime is a P group, right? Its order is a power of P, and orbits, their sizes divide the size of the group that's acting, right? So if you take an orbit which is not a single point, you're getting a power of P, right? You're getting something divisible by P. And so the point is that what you conclude is that the the size of G mod H prime is equal to the number of singleton orbits plus something divisible by p, plus let's call it, right? So, the sum of the sizes of all the orbits which are not singletons, but we've just shown they're all divisible by p. So let's call it plus m, where p must divide into m, right? So that's what's happening. But as we just noted, p also does divide G mod H. So this is just a classic kind of argument in this kind of subject. You have just a bunch of formulas coming from counting, and you use various divisibility relations. So p divides G mod H, and so those things together imply that p divides the number of singleton orbits. Okay. So now it could be that the set of singleton orbits is empty, that number is 0, but that's clearly false because H prime itself is a singleton orbit, right? Remember, what are we asking? Looking at the action of H prime on G mod H prime. So there's a coset identity times H prime. There's a trivial coset here, which is acted upon on H prime just as nothing, right? So you know that there is at least one singleton orbit. So this implies that there are non-identities. So there exists a singleton orbit, aka a fixed point, x H prime, such that x is not equal. X is not in H prime, right? There's a non-trivial, right? A thing that's orbit of size 1, but which is also not just identity times H prime, not just the trivial thing. And so what do these two things conclude together give us? The singleton orbit, the fact that you're a singleton orbit precisely means that you're fixed. And so this implies that there exists x in the normalizer of H prime, which is not in H prime, right? So the normalizer in H prime is strictly bigger than H prime. Okay, so we have H prime strictly contained in the normalizer of G of H prime contained in G, right? And so now the point is that because this is the normalizer, we get NG H prime mod H prime is a group, and P divides the size. Okay, so it's a group because H is normal inside the normalizer. Okay, so why does P necessarily divide the size of this group? Okay, so how do we say it? In fact, maybe the best way to say it is this. So the normalizer is a union of fixed points, right? We said being in the normalizer means that x times your coset is in the fixed point. So the normalizer is the union of all of these fixed point elements, right? So let me just say this: since, so there's maybe a little argument to be made here, ng of H prime is precisely the union of x H prime, right? It's exactly a union of cosets where x is a fixed point, where such that x H prime is fixed under H prime. And so if you remove H prime from this, you get that P divides the number of these, and P divides the number of these. All right, so I'm just saying it parenthetically. Right, so it's a disjoint union over a bunch of stuff, but P divides the number of things that you're counting over. Right, and so therefore, right, and so once you remove H prime, you get the size of NGH mod H prime. Right, what is this NGH prime mod H prime? It's exactly a set, which is a union of cosets. And how many are there? Some number divisible by P. Right, so this NGH prime mod H prime actually has size divisible by P. Right, so there's a little argument here which I'm not maybe spelling out as lengthily as possible, so please feel free to ask me about it if you don't get it, but yeah, suffice to say that P divides the size of this thing. Now because H prime is normal in its normalizer, by definition, the quotient is a group, And so Cauchy's theorem tells us that it admits an element of size p. It admits a subgroup of size p. Right? So NGH prime mod H prime admits a subgroup, let's call it H, of size p. And this by the previous theorem. So this is by the previous theorem. Let's call it H tilde, just to be totally pedantic here. Okay, and then we define H. So now let H in G be, in fact, H is going to live inside the, yeah, maybe it's better to say that, yeah, in fact, H is going to live inside NG H prime. So let H inside NG H prime be, not very well written, sorry. Let that be little h in NG H prime, such that the image of H, so the class of H in NGH mod H prime is in H tilde, right? And so what's the size of this? So this is a subgroup of NGH prime, and what's its size? Its size is the the size of H prime times the size of the H tilde, right? So the cardinality of H is the size of H prime and the size of H tilde, just by the orbit quotient theorem. And this is now H tilde has order size p, and this has size p to the n minus 1. So this is exactly p to the n as claimed. So we actually beat ourselves a little bit. Not only can you find a subgroup of size p to the n, but you can find it inside the normalizer of a p group of smaller order. Yeah, so that's the first Philo theorem. So that's the first big one. It's actually the main, in a sense, the hardest one, I think. So you admit a subgroup of order p. Okay, and so now you make the crucial definition. It's kind of cool. Definition, let p a prime. A p Philo subgroup of G, right? Our finite group G is a subgroup P and G, such that the order of P is P to the n. So it's a P group with respect to P. So it's a subgroup order of P is P to the n. And if I look at order of G on P to the n, that's something that's not divisible by P. In other words, it's a P power. A Philo P subgroup is what? P Philo subgroup is what? It is a subgroup of prime power order, which has the biggest possible prime power order. Right? The size of any subgroup divides the order of the group. And so if you take G and you factor it and you fix your 1 prime, any subgroup that occurs that has the P to that highest power is a P Philo subgroup, right? Because G mod that power of that prime is not divisible by P any longer. Okay. So these P Philo subgroups really kind of determine the structure of the, well, determining their structure tends to be extremely important in finite group theory. In fact, it turns out the sort of second Philo theorem says that they're all conjugate tests. So the next big theorem is, and I'll prove it in 2 steps, but I'll just state it now. Let P and Q 2 P Philo subgroups. Then P and Q are conjugate. Then there exists G and G such that G P is Q. Okay, so two P Philo subgroups are conjugated to each other by the action of G. So that means P Philo subgroup is not unique. It's not necessarily normal, anything like that. But any two of them are kind of the same, right? That you can twist by some element. You know, conjugation is this very nice, it's like an automorphism of the group, right? And it takes one to the other. So any two of them really have the same structure in some sense. Okay, So before we prove the theorem, let's prove a proposition, which almost proves it along the way. Let P be P silo, and let H in G, order of H is P to the S, less than or equal P to the N. So let H be any P group that lives in G. As we know, there's lots of them. Then there exists G in G, such that G inverse is contained in P. So this is actually almost the same thing, right? Because in a minute, H and P are going to have the same size. But for now, this is actually a stronger thing. I guess this is also sometimes called the second Silo theorem. Well, they're kind of equivalent. Anyway, right? So you can conjugate any P group into your big P. Okay, so let's prove the composition, the proposition. So again, we're going to let G act on some clever, kind of funny coset space. And in fact, no, it's not actually coset space. It's actually the set of conjugates of P in G. So let X be the set of subgroups, let's call them Q in G, such that Q is H inverse for some H in G, and this is the orbit. So this is the orbit of G acting on subsets of G by conjugation. So it's the orbit of, so what is it? The orbit of P, say it a little more precisely, it's the orbit of P via what? So G has this conjugation of action on itself, conjugation action on itself. That means that there's a set which is the set of subsets of G. G also acts on that by conjugation, right? Because if I can conjugate an element, I can conjugate a subset. Okay? And so this X is actually just an orbit and under this action. Namely, I take P, that's a subgroup of G, it's a subset. I let G act on it by conjugation. It runs through some orbit. That's a great orbit to have. That's what we're going to call X. All right. Now, again, we want to play some games with the size of X. And so the thing to note is that the cardinality of X is not divisible by P. So the cardinality of X is the size of this orbit, which is the size of G divided by the size of the stabilizer of P. Okay, now what is the stabilizer of P? Well, I don't know, but it's a subgroup of G that contains P, right? So this is a subgroup of G contains P. Because whatever happens, if I take an element of P and I conjugate it by the group P, I get P, right? A subgroup conjugates itself to itself, right? It's fixed under multiplication on both sides and inverses. So this P has a stabilizer in G, which is some subgroup of G. I don't know what it is, but it's a big old group that contains P. So since this is G mod some subgroup containing P, its order divides the order of, well, I mean, yes, that's right, actually. Its order divides the order of G mod P. So order of O divides the order of G mod P, and by definition, P was a Silo subgroup, a P group of highest possible power. So this is not divisible by P. This is not divisible by P. And so this implies, the whole thing together implies that the size of X is not divisible by P. Okay, the size of X is not divisible by P. Okay, so now we're going to play a similar game to last time where we look at conjugation action. So now let H act on X by conjugation. Okay, so we're going to look at some fixed points, that whole game. So H acts on X by conjugation. Now H is a P group. All of its non-fixed orbits have size powers of P. But X is not divisible by P. And so there must be a fixed point. So since orbits of H, orbits under H are divisible by P, right, you split it up into all these different orbits. Sorry, when I say orbits, non-singleton. So since orbits which are not singleton sets, not size 1 sets, have size divisible by P, then, and this whole space is size not divisible by P, you got to have some singleton orbits. So this implies there exists fixed points of H acting on X, right? Now what was X again? It was some crazy orbit space. What was it? The orbits of G of the orbit of under G acting by conjugation of P. So it's all the conjugates of P. So what does a fixed point mean? So there exists some GPG inverse such that it's a fixed point under the action of H. So H H GPG inverse is contained in GPG inverse for all H in H. Right? So that's sorry. That's a little white lie. I need to do it that way. When I conjugate anything in GPG inverse by H, I get something contained in GPG inverse. So this is the same as saying that H is contained in the normalizer of GPG inverse in our big ambiguous group G. Okay, but it's very easy to see, and I'll leave it as an exercise to you, that group is equal to that. That's a very simple exercise with conjugating. So H is in there, and so this implies that G inverse H, G is in the normalizer in G P, right? And so this is saying for all H in H, right? So G inverse HG lives inside. Now we want it to live inside P. We're saying it lives inside the normalizer, okay? But G inverse HG is now a subgroup normalizer G of P, and this subgroup has size divisible by P to the S, right? Size divisible by P. And so now what's going to happen? This normalizer of G, if I were to quotient out by P, I would get something, because remember P is CeLO, it has the maximum possible prime power. If I were to quotient out by P, I would get something of size not divisible by P. And so this thing has to act, but this thing has size P to the S. So this implies, maybe the better way to say it is, so if I take the inverse image, the image of this group in NGP mod P, and now this is a group, so this is a subgroup of a group, subgroup, right? Why? Because this is a normalizer, P is normal inside NGP, and so I can take the image of this in there, and its size not divisible by P, right? This is a group whose size is not divisible by P. This is a subgroup, and its size is P to the S. So that's obviously a contradiction, or excuse me, its size is it's the image of a group H, which has order P to the S. So its size is a power of P, and so this is a contradiction unless. Right, you run into a contradiction unless. Sorry. In fact, G inverse HG bar is E, right? Unless you're trivial inside this subgroup, which is of course if and only if G inverse HG is contained in P. Right? When do you go to trivial in this quotient group? If and only if you are equal to the identity. Okay, so the proof required some work here. It definitely required some orbit calculations and forcing a bunch of things to fix points via sizes, and then eventually forcing this thing to be in the normalizer. So again, we did not just find the conjugation somewhere. We found we found this subgroup that had to live in the normalizer, which is not obvious that has to exist. So this statement, the tough statement, is very hard. And then anyway, it follows that that's contained in P as we claimed. Okay, and so now the proof of the theorem, the actual second CELO theorem, that any two CELO subgroups are conjugate. Well, I'll say second CELO. Okay, well, there exists G and G such that G inverse P, G, is contained in Q. But the cardinality of P, which is the cardinality of this thing, of course, is the cardinality of Q. Right? They're P CELO subgroups. They're the same. They're the same size. And so this implies that G inverse P, G is Q. Okay. So that's the second CELO theorem. It's kind of the same. I mean, follows immediately from that. Okay. There's this third CELO theorem, but since I'm over 30 minutes now, which again I think is really a full class most of the time, I am going to stop. As you guys know, the homework is due soon, and there are testing materials coming up shortly. So please jump on Piazza and let me know all your questions and comments, and I'll get back to you, pretty quickly. I'm on there. I'm on there decently often. And Monday, Wednesday, Friday, I'm on there during class time and stuff. So anyway, okay, thanks guys. Talk to you soon.